Okay, so this standard, the ISIM standard, will be a very important guideline for the laboratory and the field testing of rocks. There are some important points for the standard test of rock mechanics for the uniaxial compression tests. The first will be the shape. As I tell you, the strength of material will highly related to the sample size. With larger size, you will have a lower strength. So you need to have some regulation about the size. So you can read those. I will not read this one by one. And the geometry precision have some rules. You need to solely follow this standard. And we need to have some end surface treatment. If we have some friction along the top surface and the bottom surface, that will be the end surface. If it is rough, and if you have a high friction along the interface, then you will have the influence on the testing results, not only for the rock's strength, but also on the failure type. You will have a very large influence on that. So later I will show you some end effects. If you do not have a very good treatment, then what happened? And the rocks should be stored in the nature water content. So it means you need to cover it by some material. Before I joined the university, I run my own company. I was told to use some clothes, some how to say that, like coat, like the clothes, and to cover the rock core, and then put this to the wax, heated wax, and when you take it out, then it will be solid. Then that will be waterproof. 以前我的做法是用纱布把岩芯卷起来，然后把那个用纱布卷岩，就是纱布卷起来那个岩芯，把它浸到蜡里面，就是融化的蜡里面，再把它拿起来，所以你那个蜡就包覆了你的岩芯，然后把它放到岩芯下。This will be the kind of good treatment on the storage. Okay, to keep the original status, especially for some argillous rocks, 泥质岩类 like mudstone. It will be easy to slaking. So if it's dry, wet, even though it's the room humidity, you will have serious slaking. So influence a lot on the sample quality. So they have some regulation about the treatment or the storage of the rock core. And of course, the loading rate will be very important. So this will shows you the stress control testing. So under the stress control testing, the loading rate will be within this range. That will be standard. That will be standard. We have two control way for testing. One will be the strain control, and the other will be the load control. This depends on how you make the command to the machine, to ask the machine to apply the stress. So if you are load control, then the loading rate will be this. And we were trying to measure the deformation of rocks. For soil, we were trying to measure the actual displacement outside the sample. And how to measure the lateral strain for triaxial test. Do you have the experience on the triaxial test? Not really? Triaxial for soil. How to measure the lateral strain or the volumetric strain? Load cell will measure the axial stress, right? And you were using the LVDT to measure the axial displacement. Axial displacement divided by the height of the sample will be the axial strain, right? And we were trying to measure the volumetric strain using the water flowing out or flowing in the sample. Because we have a saturated system. 所以三轴实验我们很容易量体积应变，那就是水进出试体的量，基本上就是它的体积应变。And if you have an axial stress, you have a volumetric strain. If you have axial strain and you have a volumetric strain, then you can have the lateral strain, the radial strain. Because the volumetric strain will equals to the axial strain plus 2 lateral strain. 知道我在说什么吗？知道不知道我在说什么？不知道，糟糕了。Volumetric strain will equals to epsilon 1 plus epsilon 2 plus epsilon 3. I hope you can understand this. Otherwise, I need to start from the basic soil mechanics. So this will be axial strain, and the lateral strain will be equal because you have a cylindrical sample. Okay? So we will measure the axial displacement. 我们量轴向位移，位移除以试体的长度就是轴向应变，对不对？变形除以长度就是应变嘛，轴向应变。所以你有了轴向应变，你有体积应变。体积应变来自于什么？来自于水进出试体，因为你施加应力，那试体会膨胀或收缩。那如果试体膨胀，水就流进去；试体收缩，水就流出去。所以你从进出试体的水量，你就知道体积应变。Okay? How about rock mechanics? We measure the actual load, like you say, using load cell, and we measure the actual displacement using LVDT. They'll be the same. How can we measure the lateral strain for the uniaxial compression test? Usually we will put the strain gauge. We will put the strain rosette. For soil mechanics, we never put the strain gauge to measure the strain. For rock test, it will be easy to attach the strain gauge on the rock surface. 在岩石试验，我们通常用应变计，用应变规。Do you still remember what is strain rosette? Strain rosette will be one of the possible questions in your midterm examination. Okay? Strain rosette. You can determine the axial strain and the lateral strain from the strain rosette. You already have the homework, right? 不要一副好像从来没有听过这件事情，你们都写过作业了。Because for the rock testing, usually we will have the end effect, as I mentioned before. You have the contact point between the sample and the loading system. And between the boundary or between the interface, you will have friction. This friction will behave like a confining stress. So this will be incorrect. So you will have some local effect on nearby the boundary, nearby the end. So we will attach the strain gauge at the center part of the rock core, or rock sample. Then the results will be more representative. So measure the axial and the lateral strain, you will use the strain gauge. Sometimes we will try to use the circumferential extensometer to measure it. This will be a lot of sensors to measure for the measuring during the mechanical test. The idea of the circumferential extensometer is the idea where like this. We will put the chain on the sample. And if the diameter of the sample dilate or contract, this sensor can measure like this. Do you know of LVDT? The theory of LVDT will be some metal at a different location around the circle of the electronic device. Changing direction, you will have a different signal. If the sensor was well calibrated, then you can get the displacement. So that will be the idea of LVDT. So the circumferential strain will similar to the LVDT. If the diameter grows, then it will be like this. If the diameter becomes smaller, then it will be like this. So you can measure the diameter. You will measure the changing diameter. OK， 圆周要怎么讲？有圆周，你就可以算直径嘛。所以它其实量到的是圆周的长度的变化，对不对？圆周的长度变化，你就可以换算成直径的变化。Can you understand? This will be related to the diameter. Okay, so that will be the idea for the extensometer to measure the diameter. Why we need to measure the diameter change? If you have a diameter change, then you will have the lateral strain. What is the lateral strain? Lateral strain will be the diameter change divided by diameter. Am I right? 所以径向变化，在直径方向上面的变化，径向应变，径向应变就等于你的径向的变形除以你的长度，所以就是直径。OK? I will show you some typical stress strain curves. I'm not pretty sure if you can read this or not. Right now, I worry a little bit about this. Tom, can you read this? Do you know what it is? If I tell you this will be the axial strain, this will be the axial stress, and this will be the lateral strain. Can you read this? Can you understand this? Do you know linear stress strain relation? I already showed you, right? This will be the axial strain. This will be the axial stress. If you compress a sample, then you will have a deformation, delta. And this will be the length. And the axial strain will be delta divided by length. You know this, right? This will be the definition of strain. If you apply the stress, and you will increase the axial strain, and the stress will increase accordingly. If the material are linear elastic. However, the rock is non-linear elastic. So the stress strain curve looks like this. It will be concave upward and the concave downward. So it's not linear. If you unload it will goes to here, so it's not elastic. So it's not linear. It's not elastic. Okay? Can you understand now? If they're linear, it will be like this, but actually it looks like this. It's not linear. For this side, you will have the same axial stress in the vertical axis. For the horizontal axis, will be the lateral strain. You know, for Poisson's effect, if you apply a vertical stress, then you will have a positive vertical strain. However, because of the Poisson effect, you will have a lateral strain will be negative. You will have a negative lateral strain. 给我一些微笑嘛，看着我点点头。要不然我实在这个有非常强的焦虑感。I'm very anxious because when I talk about some fundamental mechanics, everybody looks like me like this. It seems that you never hear about this in your life, or you don't really care about this. I worry about this a lot. If you compress the rock vertically, then the rock will expand. Poisson effect. Okay? So if you have a positive strain, you will have a negative strain laterally. So this will be the lateral strain. So lateral strain will neither linear. Okay? If it is linear, if it is linear, if it is like this, what is Poisson ratio? 如果有这样子轴向应变、侧向应变 ，what is the Poisson ratio? Axial strain. Axial strain. Lateral strain divided by axial strain. If we have this graph, if you have this graph, you will simply divide the slope of this by the slope of this, because the axial stress will be the same. 所以 Poisson ratio 是什么 ？Poisson ratio 其实这个斜率跟这个斜率的比值，这个斜率除以这个斜率就是 Poisson ratio. Okay? And here, shows you some definition of some elastic constant. For linear elastic material, we don't really need to care about the definition because it's a linear elastic, so you already know it. But this is not a straight line. Since it is not straight line, then you will have a lot of definition to talk about the elastic constant. Because actually you don't really have an elastic constant. Understand? So the first will be the tangent Young's modulus. So we will try to get the elastic part to draw a straight line, and the slopes will be the tangent elastic constant, tangent Young's modulus. Or another approach, we will unload the rock, and we will try to use the unload slopes as the tangent elastic constant. Usually the unload part will be more linear, but it's not really linear, but it will be more close to the linear, more close to a straight line. OK， 这里告诉你怎么去得到就是所谓的切线那个 Young's modulus 啊，你会找就是应力应变曲线，开口向上，然后接着有一个线性段，你会去用那个线性段的斜率当成你的切线弹性常数。那另外一个方式就是解压，然后你会用解压的那个直线去当成你的切线的弹性常数。The other will be the second Young's modulus. The second Young's modulus will connect this point and this point, and the slope of this straight line will be the second Young's modulus. And the average Young's modulus will more close to the tangent Young's modulus. Okay. And I already mentioned this before. And I also tell you how to evaluate the Poisson ratio from the curves. So that will be using the straight line portion, and you will have two slopes, and the difference and the ratio between two slopes will be the Poisson ratio. Okay. So the Poisson ratio for the previous rock specimen could be around 0.3 to 0.4 according to the definition, because it's not really linear elastic material. So you need to see what kind of elastic constant you have and what kind of Poisson ratio you have. I already mentioned this to you. So if you have the axial strength and the lateral strength, then you can have the volumetric strength. So for the previous specimen, you can calculate the volumetric strength will be this. So it means the volumetric strength will be positive. So the rock is contract. The volume of the rocks will be contract. I will show you more details of the stress strain curve of rock specimen. This will be the typical stress strain curves. The right hand side, you already done this. The left hand side will be the stress strain curves, and the strain will be the lateral strain. Okay, so here will be the axial strain, and here will be the lateral strain. The material I cover here is mainly come from the textbook of Goodman, and I think this is very worth to mention to all of you. So please focus on this, because this will be your examination next week. That will be your question for next week. Okay? Please believe me when I say this will be, it means I mean it. Okay? Why? First, I will give you the reason why I think this stress strain curves will be important for all of you. Do you know the deformation and the failure mechanism for soils? Usually, we will talk about the soil deformation from the micro point of view. If you learn soil mechanics, you will learn it from the very beginning. How the soil deformation occurs? It's mainly occur at the contact point of soil grain. You will have an elastic deformation. If you have two balls, you put the ball approach to each other, then you will find a circle, right? And if you apply larger stress, the circle will become larger and larger. The contact area will increase. And these two balls will close to each other more and more. Correct? So that will be the deformation. If you unload it, the contact area will decrease. If the ball is elastic material, when you unload it to zero force, then it will be go back to the original condition. Okay? Sometimes the soil will not only be the rounded grain. For clay particle, you will have the platy grain for soil. It will be plain-like. So sometimes you will have a deformation like this. Under stress, this platy mineral could be deformed. If you remove the load, the shape will going back to the original location. So this will be the elastic part. Okay? But we both know the soil mechanics, we have a lot of plasticity. And we always said the soil will have a memory. Right? Did you ever heard about this? The soil will remember the stress history subject to the soil. So that's because of the plasticity. And if the soil subject to shear stress, then you will have a plastic strain. How the plastic strain occur? Generally, the plastic strain or the irreversible strain is mainly comes from the relatively sliding and rotation of grains. 塑性应变哪来的？塑性应变来自颗粒和颗粒之间的相对滑动跟滚动。If the particle sliding up, if you remove the load, the particle cannot going back to the original position. So that will be the source of plastic strain. Okay? So that will be the soil mechanics. How about rock mechanics? How about the stress strain curves of rocks, especially for intact rock? There is not so much contribution from the contact of grains, because you already have a lot of cementation within the rounded grain. It will be a little bit difficult to have the grain sliding or grain rotation for rocks. For crystalline rocks, you have a very good interlock between the grain, like granite. It's different from the sand. So where the deformation comes from? Actually, for rock mechanics, the deformation came from microfracture. So that will be the reason why I tell you, I think, to my opinion, this plot will be the most important, one of the most important plot for students to understand the basic difference between soil and rocks. Okay, so I will come back to this plot. We divide the stress strain curves into several regions. From O to A, we will have a curve, concave upward. Can you see it? 有一个开口向上的非线性段。After this, you will have a linear part. The stress strain curves will be a line, will be a straight line. And actually, we divide this into two parts. From A to C will be generally straight line. But actually, we will divide B here. I will talk about this later. Okay? From A to B and B to C, you will have a straight line. Beyond the point C, the linearity will be destroyed. So it became concave downward. 过了 C 点，不再线性，它开始开口向下。Do you still remember what is the point C is for the previous slides I showed you? We called it what do we call it? Nobody listened to me. We call it the yield point, right? Y-I-E-L-D, yield point. And the slopes of the stress strain curves keeping decrease. It means the stiffness of the rocks keeping decrease， 它的进度一直在下降，因为它的弹性常数一直在下降 ，until it goes up to the peak strength point D， 终究达到了它的最大的能够承受的应力低点。Go beyond the point D, the stress drop dramatically to the lower point and goes to the receiver. Okay? So I already showed you some definition already, right? If you listen to me, if you don't listen to me, I don't know how to teach you. Okay. Goes back to the point B. Like the actual strain versus deviatory stress, or actual stress actually. The curves will concave upward, the same, like this. Above point A, you will have a linear part for the lateral strain versus axial stress. Beyond point B, here, the curves will start to become concave downward. This is not similar to the plot on your right-hand side. Above point B, you still have a roughly straight line. But from the axial stress and lateral strain, you can see the straight line will be broken or be destroyed when the stress goes up beyond point B. Okay? Then the rest of the behavior will a little bit similar to the right-hand side. Goes up to the peak stress and the lateral strain keeping increase, it will be expansion, and going down to the residual condition. How to explain the observed stress strain curve? How do you explain it? We try to use a very useful advanced tools to acquire, to get some important data or important evidence to say the whole story. We call it acoustic emission measurement. When I was the PhD student, my advisor told me to have my PhD thesis working on the acoustic emission. But finally, I did not follow his suggestion. Okay, the acoustic emission, the idea is put a lot of geoform around the rock sample. When you apply a load on the rock, then you will generate microfracture. Every single microfracture will generate the elastic wave like an earthquake. So you have a lot of geoform, then you can receive every single event. And you can try to use the way to locate the epicenter of earthquake. You know how to how to evaluate the epicenter of earthquake? If you have an earthquake, then you will have a wave generated to the ground surface. And if you have a three-state strong motion station, you can use in the arrival time to this three strong station to determine where is the source. The same idea, the acoustic emission can do it the same way. So we can quantify the microfracture evaluative process. So all the story I tell you will mainly based on the evidence from the acoustic emission. For the first stage here, you will have a stress strain curve, concave upward. Please remember one thing. If you carefully listen to me, then you can answer the question for next week. I'm pretty sure, because you understand what I'm talking about. Then you can write the answer without any further reading or anything. You just carefully listen to me, and you can benefit a lot. Okay? So the concave upward means the stiffness increase. What happened? When I applied a uniaxial compression stress, like I mentioned to you, you will have the end effect. So it looks like you have a confining stress subject to the sample. And you have a vertical stress applied on the vertical direction. If you have some horizontal fractures, those horizontal fractures will tend to close. Okay? Because the confining stress, pseudo-confining stress, and the compression stress to make the horizontal fracture close. So the stiffness of the rock start to increase. If the stiffness increase, what happened? Stiffness increase means the slope will increase. What is stiffness? Stiffness will related to the modulus, will related to the elastic constant. So when we talk about the stiffness increase, it means the elastic constant increase. What is the elastic constant? Elastic constant will be the slope of that curve. So if you have the joint, you have the microfracture closing during the early stage of your uniaxial compression test, then the stiffness of the rocks will increase. So that will be the reason why you will have curves where it's concave upward. Okay? This stage, we call it the microcrack closure stage. So from O to A will be the microfracture closure stage. From A to B, it will be the elastic stage, because all of the microfracture can be closed, already be closed. So right now, the rock behaves like the ideal material. It will be elastic, linear elastic. Okay? Because it's a linear elastic, so the stress strain curve will be a straight line until to point C. But here, beyond point B, the lateral strain start to increase faster than the increment of axial strain. Can you see it? So it means above point B, the Poisson ratio will start to increase. Why? The Poisson ratio will be the slope ratio. In this part, it's still, this will be straight line, this will be straight line, so the Poisson ratio will be the identical value, because the slope will be the same. But beyond point B, the slope from here to here will be the same. But here, the slope will decrease. So the Poisson ratio increase. Okay? Above this point. What happened? What happened? Above the stress here, when the stress going up from A to B, the rock start to have the microfracture development. Because the rock already goes up to certain value, and the rock will start to have the occurrence of the microfracture. In general, in the early stage, all of the microfracture will parallel to the maximum principal stress in the early stage. So it will be reasonable. So you need to understand, if you have a brittle rocks, if you apply a compression stress, you will have a lot of vertical fractures. So there will be the observation from the failure of the rocks. So you will find that there are a lot of fractures parallel to the maximum principal stress. Okay, that will be very important idea for rock mechanics. If you have a lot of microfracture vertically, so it's a little bit look like this. If you have a rock sample like this, then pop, 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 pop. Can you understand? You will have a microfracture like this. You have a microfracture like this. The vertical stress-strain relation still elastic, but because you have some vertical crack generally, so the lateral strain start to be nonlinear. Understand? 因为你有很多这种垂直的裂隙开始这样子发育，一点一点的发育。虽然垂直应力跟垂直应变它们之间的关系还是线性的，但是垂直应力跟水平应变的关系却开始产生改变。The explanation will be the initiation of microfracture. I already tell you, I am not trying to tell you the false story here. There are evidence from the acoustic emission. Okay, so I am not tell the story arbitrarily. There are evidence. Beyond this point, we enter another stages. Okay, so we will talk about the region 2. From O to A, we call it the joint closure stage, right? From A to B, there will be a linear deformation stage. Beyond, above point B, you will have the initiation of micro cracks or microfractures. Goes up to the point C, the axial displacement versus axial load will become nonlinear. So we call it yield point. Okay? So from point B to point C, there will be a new crack start to occur. From C, above, when the stress above C, the development of this micro crack start to increase. Understand? So from the B to C, you will have a small number of micro crack. But above point C, you will stop like from B to C, it will be like pop, 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 pop. Above C, it will be pop, 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 pop. Can you understand? So that will be the difference between from B to C and above C. Okay? So above C, you goes into the stage 4. It will be increasing micro crack density. When the micro crack density increase very fast, then the stiffness of the rock sample will start to decrease. Since the stiffness start to decrease, the slopes of the stress-strain curve will become gentle and gentle and gentle. So the stress-strain curve will become concave downward. Right? I hope everybody sitting here can understand. then you can answer my question. I will ask you to draw these curves and tell me how many stages you have and what happened for every single stage. Okay, that'll be your question for next week. Please. Louder.
Where is the stress generated? What kind of thing can generate the stress to affect this type?
We have the uniaxial compression test. Right now, all the things we are talking about the axial compression test. This. We will have a sample in this stream, and we will apply a vertical load on the sample. And it will shorten, and it will expand. And we will measure the load in vertical direction. And we will measure the strain in vertical direction and horizontal direction as well. So we can plot this kind of stress strain curve.
And volumetric.
I will mention this later. Okay, thank you for your question. And during this stage, the microcrack density start to increase, and gradually you will have some collision. You will have some collision. The microfracture start to link to each other. Understand? Origin, you have some microcrack, and when the microcrack became much more, then some microcrack like this, some microcrack can be connected like this. So you will have the connection between the microcrack. So during point D, you will have the forming of a major microcrack. Okay? Then the rock cannot subject the load anymore. So the stress will dropping down to here to point E, and below point E it goes into the stages of sliding along the major cracks. This sliding will relatively have a unified strength. So it will be going into the recedure stages. Okay? Please give me 5 minutes more. I want to explain the plot below. So this will be the same. I will not provide time to talk about this. So you will have stage 5 and you will have a stage 6 here. So from here, during this stage, you will have a joint closure. You will have the microcrack closure. So the below will be a stress strain, will be the axial strain, horizontal, and volumetric strain in vertically. So in the positive direction, we always show, in the upward direction, we always show the negative volumetric strain. Negative volumetric strain will be dilated. Downward will be the positive value of the volumetric strain. And positive volumetric strain means contraction, means the volume decrease. So you can see here, in the very beginning, the volume of the rock will decrease. Why? Because of the microcrack closure. Okay? And you will have almost constant around here. Not too many volumetric change during this stage. Beyond this point, as I tell you, you start to have a pop, pop, pop. You have a microcrack. Because you have a microcrack, your volumetric strain will start to increase because of the microcrack. So, to this point, the increasing microcrack development, the volumetric strain will increase very fast because of the increment of the microcrack keeping increase. Understand? So the volumetric strain increment will start to increase. So the slope will become steeper and steeper. The rock will start to dilate. To this point, the dilation speed will become slower, slower, and slower. So for this plot, there will be a complete stress strain curve of a sample, of a rock sample. So I will not increase you detail. For this plot, somebody make some study. So all of this dot will be the generation of a single microfracture, which is measured by the acoustic emission system. Okay? I will stop here.